Every morning, it rises. It warms the soil, drives the weather, and powers every food chain on Earth. But this same star will eventually swell into a mass of plasma that consumes the sky. Right now, we are living through a long period of equilibrium. For the last 4.5 billion years, the sun has burned with a consistency that allowed oceans to settle and biology to take hold. Because a human life lasts only a fraction of a cosmic second, we experience this stability as a permanent feature of the universe. We build civilizations and calendars around the assumption that the sun is a fixed, unchanging light. While 4 billion years feels like an eternity, this window of safety is one segment of a much longer evolution. The sun's life cycle is moving toward a phase where the star begins destroying its own surroundings. Deep inside the core, immense pressure and heat force hydrogen atoms to fuse into helium. This process is the engine that keeps the star alive today. Fusion releases energy that creates an outward pressure. At the same time, the crushing weight of the sun's own mass pulls everything inward. As long as these forces match, the star remains stable. But that outward pressure depends on a stockpile of hydrogen that is steadily being used up. Every second, the core converts more of its fuel into helium ash. Because the hydrogen supply is finite, the internal balance will eventually fail. The physics of the core dictate that the current arrangement of our solar system is a temporary state. In roughly 6 billion years, the hydrogen in the core will be exhausted. Without fusion to provide outward pressure, gravity wins the tug-of-war, and the core begins to contract. This contraction creates immense heat, triggering a hotter reaction, the fusion of helium into heavier elements like carbon and oxygen. This new energy radiates outward, causing the sun's outer layers of gas to puff up into a bloated, churning mass known as a red giant. As the star's boundary pushes into space, it reaches the orbit of Mercury. The first planet is engulfed, dissolving into the outer layer of the star. Next is Venus. Its atmosphere and surface are vaporized as the blistering plasma overtakes its position in the solar system. The expansion continues, pushing tens of millions of miles across the inner solar system toward the path of Earth. The same stellar engine that forged these planets will eventually expand to consume them. Astronomers at observatories like Mauna Kea use computer models to map exactly where that expansion will stop. Their data reveals a scientific mystery. Earth's physical survival is not a foregone conclusion. Our planet is caught between two competing forces. As the dying sun bloats, it sheds mass. Its gravitational grip weakens, allowing the planets to drift outward into wider, potentially safer orbits. But at the same time, tidal friction creates drag. This saps the planet's orbital energy, pulling it inward toward the stellar surface. This chart maps these variables. Researchers track the rapid growth of the star's radius against the decaying orbital path of the planet. At this threshold, the planet either drifts into the void or is overtaken by the expanding gas. Whether Earth's crust is vaporized comes down to the precise rate of the sun's mass loss. There is a distinction, however, between the planet's mass surviving and the survival of the environment that allows us to exist. Even if Earth escapes the plasma, it will be subjected to intense levels of energy from the expanding sun. The red giant's radiation will saturate the atmosphere, raising temperatures far beyond the limits of any known biology. The oceans will boil off, escaping into space as vapor. Without protection, the planet is stripped down to a barren, scorched shell. Escaping the reach of the solar plasma is a hollow victory. Long before the sun could touch the crust, the radiation will have rendered the planet sterile. We can observe the aftermath of this process across our galaxy through the Hubble Space Telescope. In its final violent act, the red giant sheds its outer gas layers, ejecting them into deep space. These glowing materials form a planetary nebula, a colorful cloud surrounding the remains of the star. Only the burned-out core is left behind, a white dwarf. It is extremely dense, emitting only the fading heat of its former life. Any surviving outer planets will be left in the dark, orbiting this cold, distant remnant for billions of years. The rock we call Earth might outlast the expansion of the sun, but if it persists only as a lifeless stone circling a dead star, we have to ask if that truly constitutes survival.